Easy peasy now, we've done this already. What's the name of the A? Mass number. Okay. What's the name of the Z? What information did these provide? Yeah, so mass number, what does that equal? The number, now I'm just writing this for short, but this symbol means number. Number of protons, and of course I'm just writing P for short, plus number of neutrons, and then the atomic number, just go with number of protons, okay? If it'll be the same thing as the number of electrons if it's no charge, of course. All right, fine. 4 marks. B1, describe the penetrating power of alpha, and then B2 of beta. So another, yeah, I think a little bit more than just weak or strong. So yeah, that's what we're talking about, Chris. What did you say? So the first one is alpha. Can alpha even pass through paper? Yeah, I think thick paper will pretty much stop alpha, wouldn't it? Well, I suppose it depends on how many radiation. Yeah. Now alpha might go through paper, I think. Yeah. Alpha will not go through your hand. I think the key thing is your skin. Okay. So I think that's the most important thing. Alpha. Right, that's not right. Alpha, it's very hot, and my brain does not work as efficiently in this temperature condition. You know, like when you have your laptop and it gets really hot and then it starts to go slow? It's the same effect. Right, alpha will not pass through skin. Yeah.
Can you fancy it?
Make it fancy. Fancy-mify it, is it? Alpha will not penetrate human skin. If you want to make it a bit fancier. And then beta. Let's say alpha will not pass through skin, but we should say what it will pass through. But yeah, it could pass through, let's say paper, one sheet of paper. Well, how about if I say some, what if I say very thin paper? You know, but I want to say something that would go through, or maybe it won't go through anything. Pass through air. All right, maybe I'm just opening up a can of worms if I try to do this. Let's just say it will not pass through skin, but maybe through tracing paper. You know tracing paper? Yeah. It's what the kids use to when they want to copy something. They put it on top and then they draw it. You know what I'm talking about?
Yeah.
Maybe. Okay. Now what about beta? We're happy that beta will pass through paper. It will pass through. It'll pass through skin, but not through walls. Maybe. Yeah. So beta is stopped by foil, yeah. Beta will pass through skin, which makes it harmful to you. but not walls or even aluminium foil. What's aluminium? AU, is it? AL? Oh, AU is gold. No, yeah. AL is aluminium. Okay. That answers that. Alright, so just to recap, alpha will not go through skin, so that makes it okay for people to be around, although you don't want to be around it all the time. Because, you know, if you have a cut or something, or if you inhale it, it's really bad. Yeah, like, I mean, if it's in the air in dust or something, you know. If you inhale or ingest or eat alpha contaminated food, it's really, really, really bad for you. Of the three of them, alpha, beta, gamma, alpha is probably the worst one if it gets inside you. Okay. Beta will go through your skin, but because it's smaller, it won't do as much damage unless you have lots of it. And gamma will go through lots of things, and again, you don't see too much of it in nature on Earth, so you have to be around it a long time or a lot before it hurts. Well, it won't actually hurt, just damage you. The thing about the radiation is that you won't necessarily know that you're being bombarded with alpha, beta or gamma, unless it's really, really high and you start to melt. But you couldn't tell for it, like you can't, the problem with radiation is you can't smell it. You know, like there could be alpha in this and you wouldn't really know. The only way you would know is, what do you use to detect radiation? What's it called? The GM counter, yeah. That's the only really way you can tell. Okay. Right, next one now. We have to finish these formulas. Can we see them here? Can you read them out to me if you have it in front of you, someone? Okay, so this is C1. Yeah, what is it? It's Rn, yeah, okay. And what's the mass number? And then?
The number is 86.
And then what decay is it? And you have to finish it, yeah? Well, alpha, what happens with alpha? It loses 2 protons, 2 neutrons, yeah? So this becomes 1, 1, 6.
2 to 6.
Yeah, but
Yeah. And then this one here is 84 plus a helium. Oh, sorry, I've been sorry. Hang on, I'm being stupid. Of course, it does not lose 104 protons and neutrons. Helium 42. Okay, thank you. And then the next one.
AC.
A. C.
Last number is 228.
What is it?
228.
Yeah.
Atomic is 89.
So
Beta.
beta.
TH.
Now, with beta, the proton and neutron number remains unchanged.
2 to 8.
And what happens? 90. You gain a proton and lose a neutron. Yeah? No. Hang on, down that please. It's 90, isn't it?
Yeah.
Plus electron, which I write 0 minus 1. Super. Super. Okay, that's C done. So how many marks now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And just one part to do now. The D part. Okay. Good question, I think. Right. Now, it has activity of 2 mega BQ and a half-life of 12. So let's write that down. Half-life 12 and activity 2 times 10 to the 6 BQ. And just to recap what that means in 12 seconds, how many atoms have been disintegrated or destroyed in the radiation? No, just for this one. What does half-life mean? That's my question.
Time taken for half.
Time taken for half of it to disappear. Okay? So after 12 seconds, half of it is gone. Now, what does this activity mean?
The amount of
Yeah?
atoms that produced in 12 seconds.
Yes. In fact, just 1 second. You do this per second. So at the beginning, there's 2 times 10 to the 6 atoms destroyed in a second. Okay? So if you want to think about it this way, the unit BQ is like number of atoms per second. Okay? Now what is he asking for?
Activity.
The activity after 60 seconds. So you have a formula for that, don't you? Yeah. Well, first, actually, before we do anything, let's get the lambda constant. So the formula for lambda, it's at the bottom of page 2.
Yeah, lambda.
It's log 2 over the half-life. Please calculate. So log 2 over 12, what's that going to be? Like 0.07? Whoops.
0.057.
0.05.
0.577.
Now that we have the lambda, let's, what is he looking for? Activity. Now, he doesn't actually give you the formula here, and I don't know if it's in the new formula book, so let me write it down anyways. No, actually, he kind of does. You have to just do 2 steps for it. He gives us n equals n0 e minus lambda t, and he also tells us that a equals lambda n. Now, let's look at this logically for the moment. What does he want? He wants the a. Yes? Do we know the lambda? Yes. We just got it. Do we know the n? No. So we need to use this formula to get the n. Do we know the n at the beginning, the n0? No, we don't actually.
What is the end?
The n is how many atoms you have. Okay. So in fact, what I should do first is, before I can use this, I should use this to get what is the number, the n0 at the beginning. Okay. So a0 equals lambda n0. So if I divide by lambda, do I know a0, the activity at the beginning? I do, don't I? It's this, yeah. So it's this number divided by lambda. So can you type that in? 2 times 10 to the 6 divided by lambda. Well, no, it won't be that much bigger. It'll be like 4 times 10 to the 5 or something.
Well, 3.47 times 10 power of 7.
3 point,
47
yeah.
times 10 power of 7.
Right, so now I know the a0. Yeah? All right. Now, I think actually I was going to do this a long, complicated way, but I think I'll just make it. Yeah, I'll just actually tell you what. I'll do it a really, really easy way. Yeah, okay, no, sorry. Don't mind me. I know the n0 now. So I can now put n0 into this formula. So then I can find the n. So I know n0, I know the lambda, and what's the t?
67. No, 12.
So it will be
T is
Oh, 60.
n equals n0 times e to the power of lambda or minus lambda times t, and what's t? 60. 0.
108.
Yeah? You sure? Yeah, thank you. Times 10 power 7. Now, finally, now that I have the n, I can go back to my formula that says A equals lambda n. Lambda is 0.0577 and the n is right there. So finally, what is the A? 62,000. So if I was to do, it'd be about 63,000, is it, if I round it up?
Yes.
So 63 kilo BQ. Right?
This is second part.
Oh, dudes, I've already done the second part. Determine the K constant. So where's that? Huh?
We've done the K constant.
We've not done it.
The decay constant is called the lambda.
Is it?
Yeah. All right. So there's also the answer for part 2. Determine the initial. Oh, dudes! Determine the initial number of magnesium. So that's the N0, which is
3.5.
I didn't do this one. Determine the activity after 5 seconds, which is exactly the same as after 60 seconds. You just put a different time in. So it's 5 seconds.
We find the n first. Find the n.
First I have to find the n. So just put 5 in there, please. And tell me what you get. What is it? This is the n, is it? And then to get the a, just multiply by this lambda now, please.
1.5 is 10 by 6.
So 1.5 mega BQ. Now I've said this before. Okay, look here. I've said this before. Sometimes, and I don't understand this, but for me, sometimes it's easier almost to do some questions backwards. And this is a good example of it. It was much easier to do this part and this part before this part. I think so anyways, for me. It makes more sense logically. And then part 4 is the same as part 1. So again, like we've seen before, they can ask you to do the same thing twice. Yeah? Are we all cool?
That's the final answer.
This one?
Yeah, yeah.